airport plays a very important role in the economic development of the country. In regards to the same, it is important that the airport becomes usable and is free from obstacles in point of view of operation of the aircraft. So here in this presentation, we are going to learn about the standard and recommended practices of Icao ANNEX14 and a chapter which deals with the obstacle restriction and removal. So let's move towards learning how these surfaces are defined. Before we start further in regards to the surfaces being designed and defined, it is important for us to know what are obstacle limitation surfaces. The obstacle limitation surfaces are a series of imaginary surfaces that defines the volume of airspace at and around the airport to be kept free of obstacles so that the aeroplane operations can be conducted safely and to prevent the aerodrome from becoming unusable. So what role does the obstacle limitation surface play? We all know the development cost of an infrastructure for a bigger airport will have a huge financial investments. So in order to effectively utilize the designed aerodrome, it is important to develop the obstacle limitation surfaces. So in case if there are infringements to these surfaces, this will lead to have an impact on the operations of the aircraft. That is, in case that the larger aircrafts do tend to operate from that particular aerodrome, it increase in the height of the obstacles will lead to changes into the declared distances, and also the infringement of these surfaces by obstacles will lead to changes in the flight procedural designs of that particular aerodrome. This may have an impact of minimum clearance altitude of the aerodrome or the minimum sector altitude of the aerodrome. So this is the reason why the obstacle limitation surfaces are designed in terms of the aerodrome. With the introduction of the obstacle limitation surfaces, now you would be keen to know on how these surfaces are being designed or calculated. It is based on two aspects. The first is the type of runway. The second is the intended operations to take place. Each airport or each runway which is designed will have a critical aircraft for its operation. So the critical aircraft features of the critical aircraft as provided by the manufacturer of the OEM of the equipment will help in designing the runway along with its various allied infrastructures such as taxiways. So this is basically referred as aerodrome reference code in international standards. Now aerodrome reference code is basically alphanumeric representation of the aerodrome capacity with which it can operate, or the capability of the aerodrome. The second is intended type of operations. This is basically an identification of the type of approach procedures to be followed. It is maybe it is visual, maybe it is non-precision based, maybe it is precision based approach systems. So now how do we calculate the aerodrome reference code? Now aerodrome reference code is alphanumeric representation of the capability of the airport, as I told you in the previous slide. Now it is based on two elements. That is, first element is the aeroplane reference field length, and second is the wingspan category. So an aircraft which has got a wingspan of up to but not including 15 meters. That means in case if an aircraft has wingspan of 14.98 meters will also be considered or will be considered as category A. Similarly and likewise, you will have code letters for each aircraft with its wingspan. And what do we mean by aeroplane reference field length? So aeroplane reference field length would be introduced to you in the next slide, which gives you an understanding of key things which we have to remember. The key points to remember: the aeroplane reference field length. As we spoke about in the previous slide, aeroplane reference field length is the minimum field length required for the takeoff at maximum takeoff mass, standard sea level conditions, at still air, and zero runway slope. So this would be prescribed by the aeroplane manufacturer or the OEM of the aircraft, which would be approved by the certifying authority of the manufacturer's country. So the field length is the balance field length for the aeroplanes if applicable, or the takeoff distance in other cases. So that means the aeroplane reference field length is basically an understanding that gives you the takeoff length required. We all know the performance of the aircrafts variate with respect to the altitude. The airports would be designed in such a way that it calculates the takeoff distance of the critical aircraft to get operated from that airport or the runway. Second is the runway strip. So what do you mean by a runway strip? Since most of the calculations would be either based on the runway strip or on the runway. So a runway strip is defined as an area including the runway and the stopway. Stopway, if provided, intended to reduce the risk of damage of the aircraft running off a runway and to protect the aircraft flying over it during takeoff and landing operations. So this is the key points to remember before you start identifying about the or understanding about the obstacle limitation surfaces. Now, next we move a picture which gives you an understanding of the obstacle limitation surfaces or why it is needed. So I'm taking a picture of a runway which is located at Delhi's International Airport. So here you see there are two sets of two straight lines visible which are white in nature. So let's move and understand. In the next slide, I show a point where the runway is starting and you have got a displaced threshold. That is a threshold which is not located on the extremity of the runway. So thereby, in the previous slide, when you see the runway is available of such length that half of it is being displaced due to the growth of obstacles. So this may have an impact on the effective utilization of that particular runway. So let's see. What are the types of surfaces which are being designed? Now, these are namely the outer horizontal surface, the conical surface, the inner horizontal surface, the approach surface, the inner approach surface, transitional surface, the inner transitional surface, the bulk landing surface, and the takeoff climb surface. So these are the types of surfaces which are being designed. And to my right, I see a figure that gives you a type of surface, how it is being defined, right? So let's see surfaces one by one. So in the picture, you see a black strip, which is known as the runway strip, or which is shown as the runway strip here. So few surfaces are defined based on the runway surfaces, either the runway strip or the runway itself. So let's understand how these surfaces are being designed. So the first surface which we are going to see in this presentation is the transitional surface. The transitional surface is the first surface when we move laterally from the runway strip. So what is the definition of a transitional surface? The transitional surface is a complex surface that extends along the side of the strip and part of the side of the approach surface that slopes upwards and outwards to the inner horizontal surface. Now, this is slightly tricky. It's a surface that is run parallelly to the runway strip, parallel to the runway center line, where it meets the approach surface and the inner horizontal surface. So the limits of a transitional surface are a lower edge and an upper edge. So what is the lower edge? It begins at the intersection of the inner horizontal surface with the approach surface and extends down the runway parallelly along the runway center line or the extended portion thereof. And where does the upper edge fall? The upper edge falls on a plane which is located on the inner horizontal surface. So what would be the elevation of a point? At the lower edge, it would be equal to the elevation of the approach surface at that point. When it is along the side of the strip, this would be equal to the elevation of the nearest point on the center line. So when we slope upward and outwards, farther the distance we go from the runway strip, we can increase the height of any aids or equipments to be placed along the side of the runway. So the slope of a transitional surface shall be measured in a vertical plane at right angles to the center line of the runway. So that means the slope is basically calculated at a vertical plane. Now, what is this surface designed for? This surface is basically designed for the airspace above the areas on the final approach to land phase maneuver of the aircraft. When the aircraft is closer to the airport, it is required for preventing this airspace of any infringement till the time the aircraft is on the runway, safely on the runway. The table in this slide gives an indication of the slope of the transitional surfaces with reference to the runway classification types. As per the given table, when you consider seeing the slope of a transitional surface when it is a precision approach category number 1 for runway code element 3 and 4, the slope given is 14.3%. So this implies that every 7 meters I move farther away from the runway strip, there would be a height increment by 1 meters with reference to the base datum. So the inner horizontal surface is restricted to a height of 45 meters with reference to the elevation datum. The total distance to reach a height of 45 meters would be at a distance of 315 meters from the edge of the runway strip. When we move farther from the transitional surface, the next surface which we come across is the inner horizontal surface. Now, before moving on how this surface moves or tends, we have to know the certain characteristics of inner horizontal surfaces. It is a surface which is located in a horizontal plane above an aerodrome and its environment. The radius or the outer limits of the horizontal surface will be measured with reference to a reference point or points in case if it is established for such purposes. So the shape of inner horizontal surface may be or may not be circular in nature. The height of the inner horizontal surface will be measured above an elevation datum which is established. The purpose of the inner horizontal surface is to protect the airspace around the airport for visual circling prior to landing. So, for smaller aircraft, it may not be required to have or design an elliptical surface. However, for the larger aircrafts, it becomes essential to have a racetrack pattern. The choice of the datum may not be essential when the runways are found to be level. However, the datums may be defined when the elevation of the runway is more than 6 meters. So in this case, the datum may be more than 1. And for complex surfaces, a common elevation may not be mandatory. But however, dominant restriction will be considered, or dominant height restriction would be considered with reference to the same. So this table shows the height restriction of in a horizontal surface with respect to the distance at which the horizontal surface is defined. So for a non-instrument runway, code element number 1, it would be 2000 meters and extends up to a distance of 4000 meters based on the classification of the runway. So in the previous slide, we came to know the restriction of height and the distance at which the inner horizontal surface is designed. This slide will give you an understanding of how the imaginary IHS, or the inner horizontal surface, is basically designed. So now for a single runway, there would be 2 reference points at the extremities. From there, we draw circular arcs of 4000 meters and join them tangentially to form an elliptical surface. This for a single runway, for where the code element is 4, that is where the reference field length of the aircraft is more than 1800 meters. Similarly, when you consider it for a smaller runways, the circular arcs may not give you an elliptical surface as for a longer runway. Now, the figure 2 shows the determination of 4 reference points in respect to 2 parallel runways and then joining them tangentially to create a more composite structure than being elliptical. The third image shows how the connection is being created between the 2 circular arcs and joining themselves tangentially to form an elliptical surface. Now, the next surface, when you move farther away from the inner horizontal surface, is the conical surface. This surface slopes upwards and outwards from the periphery of the inner horizontal surface. So, where would be the lower edge here? It would be on the periphery of the inner horizontal surface, and then the upper edge at the inner periphery of the inner horizontal surface. So now, the slope of the conical surface will be measured in a vertical plane perpendicular to the periphery of the inner horizontal surface. So these are the characteristics of the conical surface. So the table here shows the slope of 5% and a height of 100 meters for precision approach category 1, code number 3 and 4, and precision approach category 2 and 3 with runway reference codes as 3 and 4. So that means when you move farther away from the runway center line, the height at which you receive 100 meters of 100 plus the 45 meters of the inner horizontal surface. So this gives you a total height of 145 meters at the end of 6 kilometers. Mathematically, when you move farther away, 5% slope will give you every 20 meters you move out from the inner horizontal surface, you'll get 1 meters increment. So at the end of 6 kilometers, you'll receive to a total height of 45 from the inner horizontal surface and 100 meters added up to it to give you a value of 145 meters. The outer horizontal surface. The outer horizontal surface extends up to a distance of 15 kilometers with reference to the aerodrome reference point. The example shown on the right is a typical example of aerodrome reference point being co-located on the midpoint of the runway. So these surfaces are designed to maintain the safety of the aircraft when the aircraft is carrying out visual circuit during approach, departure, or while carrying out a missed approach climb. So this extends outside the periphery of the conical surface on all sides. This area is prepared in such a way that the obstruction markings, lightings and notifications being inconspicuous from the pilot's perspective when the aircraft is flying over these areas. So hence these surfaces are to be designed in such a way that the area is free from all obstacles while the aircraft is in flight. The next surface which we are going to see is the takeoff climb surfaces. Till now, we have seen the surfaces which are developed when we move laterally away from the runway. Now, when we move on to the approaching phase of the runways, we have got two surfaces, namely the takeoff climb surface and the approach surface. So, the takeoff climb surface is designed to prevent the airspace above the areas of the initial climb phase and the final approach phase to land phase or maneuver of the aircraft. Now this surface is an inclined plane which is located at a specified distance beyond the runway or a clearway if provided. So likewise the other surfaces, this surface will also have an inner edge and the outer edge. So the inner edge is perpendicular to the center line and is horizontal and it is located at a distance beyond the end of the runway, or in case if it is have a clearway associated with the runway, then it starts at the end of the clearway. And this surface will have two sides which originates at the inner edge and diverges uniformly on both sides at a specified rate, and till it reaches to a specified width and thereafter continues to be at this same width throughout till the remainder of this surface. So now the outer edge would be a horizontal and perpendicular to the runway center line or the takeoff track. So the table shows here the length of the inner edge, the distance from the runway, the divergence on each side, and final width of the takeoff climb surface with its length and the slope. So the length of the inner edge for a code number 3 or 4 runway, then the inner edge would be 180 meters, that is 90 meters extended on both sides from the runway center line, and starts at a distance of 60 meters from the runway end, or in case if it is a clearway provided along with the runway, then it starts at the end of the clearway with a divergence of 12.5% on each side and extends up to a distance of 15,000 meters from the 60 meters from the end of the runway, and with a final width of 1200 meters or 1800 meters with a slope of 2% from the inner edge. So the takeoff climb surface starts at the 60 meter. From this image, it is when you see runway number 16, beyond that it's a threshold, and it starts at the 60 meters away from the threshold or the end of the runway, and thereafter extends divergingly to a distance of 15 kilometers, wherein the final width will be at 1800 meters. From there on, it extends up to a distance of 15 kilometers at the same width. Okay, so this is the takeoff climb surfaces. So the next surface which we are going to see is the approach surface. This is an inclined plane or a combination of plane which precedes the threshold. This surface is designed in such a way in order to clear the obstacles in the approach area of the airport. So the limits of the approach surface will be an inner edge and outer edge, again as we saw in the takeoff climb surfaces. The inner edge would be of a specified length which is horizontal and perpendicular to the runway center line and diverges uniformly on the both ends of the inner edge, and the outer edge being parallel to the inner edge, which is horizontal and perpendicular to the runway center line, which is extended. Now there would be a variation in case if there is a lateral offset or an offset or a curved approach being utilized. So the surfaces will also have an impact when there are lateral offsets or any offsets. In specific cases, the elevation of the inner edge would be equal to the elevation of the midpoint of the threshold, and the slope of the surface shall be measured in a vertical plane containing the center line of the runway and shall continue in containing the center line of any lateral offset or a curved ground track. So in case of the approach surfaces for a precision approach category, runway code number 3 and 4, and the precision approach category being 1, the length of the inner edge would be of 280 meters, that is 140 meters on the either side of the extended center line, and starting at a distance of 60 meters from the end of the runway, or in case if there is a clearway provided, it starts from the end of the clearway with a divergence of 15% on each side, therefore making it into a triangular funnel which makes the airport surface approach surface. So the approach surface is further subdivided into 3 sections, wherein the first section adjacent to the runway, or which starts at the end of the 60 meters of the runway, will have a length of total 3000 meters with a percentage slope of 2%. Thereafter, the second section extends up to 3600 meters from the edge of the first section with a slope of 2.5%, and the last section will have a total distance of 8400 meters with no slope. So when we calculate the 2% slope, that is at the end of the first section, will have a height of 60 meters of the buildings. Thereafter, at the length of 6600 meters away from the inner edge, you will have a slope of 2.5%. So 60 plus another 3600 meters of 2.5% slope, then that means another 90 meters gives a total height of 150 meters. So from a distance of 6600 meters from the inner edge of the approach surface till 15,000 meters, there would be constant height of the buildings at 150 meters. So the next surface which we are going to see is the obstacle free zone. The 3 surfaces, namely the bark landing surfaces, the inner approach surfaces, and the inner transitional surfaces, forms the obstacle free zone. This is the zone which is called as the volume of airspace in the immediate vicinity of the precision approach runway, which is to be kept free of all obstacles except those aids or the navigational aids which would be mounted on a frangible objects in order to perform or safeguard the aircraft in case of balk landing or rejected landing at low altitudes. The inner approach surface, a rectangular portion of the approach surface which is immediately preceding the threshold. The limits of the inner approach surface will have an inner edge coincident with the location of the inner edge of the approach surface, but it will have its own specified length. The two sides originating at the ends of the inner edge surface and extending parallelly to the vertical plane containing the center line of the runway, and the outer edge parallel to the inner edge. So the inner approach surface is basically carved out of the approach surface with a specified width and a length and is a rectangular in shape, which will have a slope of 2% for these areas, which should be available free of obstacles when the aircraft is doing the final approach phase in the last segment of 1 kilometer away from the runway. The inner transitional surface is the next surface which we are going to see. The inner transitional surface is a surface which is similar to the transitional surface but has a difference in the limits of the lower edge and the upper edge. In the transitional surface, the lower edge begins at the end of the inner approach surface and extends parallelly along the runway till it meets the inner edge of the approach surface on the other side. Whereas for an inner transitional surface, the lower edge begins at the end of the inner approach surface and extends down parallelly to the runway center line till it meets the inner edge of the bulk landing surface. The upper edge, as the transitional surface lies, it lies in the plane of inner horizontal surface. The elevation here at the lower edge along the side of the inner approach surface and the bulk landing surface would be equal to the elevation of that particular surface at that point, and when it is along the strip, it should be equal to the nearest point of the runway center line. The slope of the inner transitional surface shall be measured in a vertical plane at right angles between the center line of the runway. Now, the table shows the slope of the inner transitional surface, which clearly states that for a precision approach category runways, the obstacle free zone have to be developed. So the slope of inner transitional surface is at 33.3%, which means at a distance of 135 meters from the runway center line, you will have a height restriction to have the climb gradient of 3.3% of the aircraft. So this is a typical example of the obstacle free zone with reference to the runway which is provided. So now the inner edge of the approach surface, or the inner approach surface, is the surface. The inner transitional surface meets the inner edge of the approach surface on one side and extends down parallelly to the runway and meets the bulk landing surface on the other edge. So the transitional surface meets the approach surface on both the ends, that is, forms the lower edge of the transitional surface. So the next surface which we are going to see is the bulk landing surface. But before we learn about bulk landing surfaces, we have to know about what is bulk landing. A bulk landing is a landing in which the landing attempt is cancelled or rejected below the decision altitude of that particular runway. We all know for a precision approach runways, we associated runways based on the categories, there is a value of decision height which is fixed. So in case if it is a cat 1 approach category precision approach category 1, then the decision height is 60 meters, below which the aircraft will continue to fly under visual flying mode. So in case if the rejection is being done, the landing attempt is being rejected at this point, this is called as bulk landing. So this is a bulk landing surface is an inclined plane which is located at a specified distance after the threshold extending between the inner transitional surface. So this surface is not preceding the runway, but it is on the runway. So it extends at a distance of 1800 meters from the location of the threshold, wherein the limits of the inner edge would be horizontal and perpendicular to the runway center line, and the two sides originating from the inner ends diverging uniformly at a specified rate from the vertical plane, and the outer edge were parallel to the inner edge located in the plane of inner horizontal surface. So similarly, this surface will also have elevation of the inner edge equal to the elevation of the center line of the runway, and the slope of the bulk landing surfaces shall be measured in a vertical plane containing the center line of the runway. So the table here shows the dimensions of a bulk landing surfaces which is located at a distance of 1800 meters from the distance of the threshold and diverges uniformly on each slide by 10% with a slope of 3.33%. So this is the bulk landing surface dimensions. So this figure is an extract of the GSR 751E, which lays the guidelines with reference to the Indian subcontinent. In this figure, you would see there would be an additional surface which has been developed called as outer conical surface. This surface is at a distance of 6 kilometers from the end of the runway and extends up to a distance of 9.1 kilometers to the end of the runway at a specified slope of 5%. Now, The inner horizontal surface extends up to a distance of 4 kilometers as we previously saw in the presentation. Now, when we move farther away till a distance of 9.1 kilometers from the runway end, the restriction of height moves up to a distance of 300 meters above the aerodrome elevation. So at this point, when you calculate the distance, when you move farther away from 4000 meters, there would be an increment of 5 meters every 100 meters, extending till a distance of 9100 meters. So the elevation at 9100 meters would be a total of 300 meters. Likewise, there is an additional surface which has been developed at a specified divergence from the outer conical surface till the outer horizontal surface at a specified divergence rate with a slope of 14.3%. We will discuss about this in our next presentation, which would be based on GSR 751E. Till then, this is